Hello, my name's Tom. I'm with the University of Technology, Sydney, and I'm here to present our paper. Well, you can read it for yourself. It's quite long. So this was done in collaboration with Data61. And we are looking at a way to generate adversarial examples. Now, firstly, what is an adversarial example? Well, maybe some of you have heard the term before. But basically, an adversarial example is a bit of text which is designed to trick another model. So in this conference, we've talked about sentiment classifiers a bit. You know, sentiment classifiers take in text and they output, you know, if the text is happy or sad or neutral, sometimes an emotion. Now, these models are quite fragile in that small changes in the input text can elicit big mistakes in the model. And adversarial examples are designed to exploit this. So here's an example. What we have on the screen is a movie review. You can read the top box there. So it's talking about a Chinese director and their film. So what the first example below it of an adversarial example does is just change a single letter. So it's changed the letter C to an A, and the sentiment analyzer has, you know, it thinks it's a negative review, which is wrong. It's a positive review still. And this is, you know, what we call a visually similar adversarial example, in that it's intended to kind of look similar to the original one, just with one letter changed. You can also have other types of adversarial example, such as a semantically similar one. So the one below it, what they've done is just change a synonym. So they've taken out the word film and put in footage to also induce a mistake from the classifier. So that's an adversarial example. Now, not every change is a valid adversarial example. In fact, what we do is define a set of constraints that specify if a given change is, I guess, accepted or not. So a common constraint is that we kind of require the adjusted sentence have the same broad semantic meaning as the original sentence. So if the original says, shall I compare V to a summer's day? You can't change summer to winter because that's not summer any longer. And this would fail the semantics constraint. Another example of a constraint is like a grammar constraint where you assume that the changed example is still correct grammatically. So if I change the word compare to compares, then it's no longer grammatically correct and the example fails. So these are just two examples of constraints. There are really as many as you can think of, but in a 15-minute presentation, I think these two are enough for now. So now that we know what an adversarial example is, let's look at some of the methods which we can use to find it. There are two predominant schools in the literature. The first one is called a token modification attack, and it views the problem of finding adversarial examples as one of optimization, combinatorial optimization. So you start off with the original sentence and you just basically flip letters, flip words over and over using some sort of search algorithm. And after every flip, you have a score and you watch the score go down using your optimization algorithm, and it finishes once you have flipped the sentiments. So this is the dominant approach in the literature. The other approach is more of a direct generative approach. So similar to, you know, our big neural networks like Google, does Google Translate and all the beautiful transformers that you've seen this conference, we just aim to, directly generate an adversarial example. So none of this flipping characters stuff. We just put in the input and treat it like a text-to-text task. Now, each of these approaches have advantages and disadvantages. So if we look at the optimization approach, well, I mean, it's pretty straightforward. Like you just change characters over and over. But as you can see, it's slow because it's not straightforward to do so. And you might change 1,000 characters before you find something. And this can take minutes or even hours, depending on how long your text is and how strong the sentiment analyzer is. The generative approach is quick. You just feed it through a model, and within maybe a second, you get lots of results because inference is quick. But of course, you have to spend all this time training the model, and that might take hours, days, depending on how long you take. You can also do really complicated transforms using the generative model, like you can summarize and paraphrase and reword things. But your word flipping approach, you're really kind of limited what you can do, because you can't really paraphrase, because by the time you flip all the words into the right order, well, your optimization algorithm isn't going to allow that. So it's really much harder to find an interesting transformation that way. This kind of leads me to the concept of transfer learning, which you all know a lot about by now, I'm sure. So what we want to do is use information we learn from another text-to-text task to try to help us with this adversarial learning task. So if you just look at paraphrasing, for an example, models who can paraphrase, they also know, they learn like a lot of useful things about the structure of text, like the start word must have a capital letter and it must end with a full stop. And if we look for commas, and that could be like a nice place to paraphrase, and just all these implicit rules which neural networks learn. And these seem like the kind of skills which could be pretty useful in constructing an adversarial example. So it really just makes sense to leverage all this knowledge. So in our work, we try to do so. And that kind of leads us to this general idea, what we're doing in this work. So what we do is we go onto the Hugging Face Model Hub, and we search paraphrase model, and we download one. And what we do is we then update its parameters by a fine-tuning process to produce adversarial examples. And we do this using reinforcement learning. So for those of you who aren't really familiar with reinforcement learning, it's like training a dog. The model tries something, and you give it a reward depending on if you like it or if you don't like what it produces. And with a dog, you might give it some food. With a model, it doesn't really like food, so you have to come up with an alternate reward, and that usually is a score. And the score of maybe 0 is an indication to the model, hey, you're not really doing anything I like. But if you give it a really positive score, you tell the model, that's good. And this is like crack to the model. It really wants to maximize this score. So that's what we do. And so it's quite a straightforward training process, because we just take the original, put it into the paraphrase model, and we can generate a whole set of paraphrases because it's a generative model. We're not really limited to a single paraphrase. And so, let's say we generate 48 paraphrases for a single example. If any of these are a valid adversarial example, then the model's done its job and it can get a good reward. So let's go into this reward function a bit more. So what we do is our reward function has 2 main components. The first one is this victim model component. So a victim model is just a sentiment analyzer we want to attack. And if our model can induce a big misconfidence in the model, in the victim model, then it gets a high reward. So we can just treat this as a number. So if our victim model is 20% less confident, then we can get a score of 2 or something like that. There's a scaling factor involved, but that's the general idea. Then you have a set of constraints which I specify. So some of those I talked about, like the grammar one and the semantics one, but then you can also include other constraints too, like the length of the sentence must be pretty similar to the original, and you're not allowed to blatantly contradict it. And you can't have these phrases in it. And if a model fails any of those constraints, it doesn't get any reward. And if it passes all the constraints, well, it can then get the juicy victim model reward, which it's promised. So over time, as the model tries over and over, it can optimize this way. The optimization diagram is kind of complicated, but it follows an algorithm called reinforce with baseline. So this is a policy gradient algorithm, one of the oldest ones from the 90s. And The interesting parts on this diagram, so we get the original, the paraphrase, it gets a reward, and there's also kind of like a baseline, like an average reward for that particular paraphrase. So the model kind of learns what a given input, its average reward is, and it can't just be satisfied with getting that reward. It has to beat that reward on each training iteration. And the other interesting part here, is a KL divergence parameter. So this little bottom bit here, we introduce a KL divergence penalty on the parameters of a model. And what that does is it stops the model drifting too far from the original Hugging Face pre-trained paraphraser. Because if you let the model drift too far, what you find is the paraphrase quality really goes down the shitter. It's you just start ending up with gibberish and not actual sentences. So we found that we really had to include this component to actually keep the model producing proper paraphrases. So let's have a look at some examples now. So let's look at the top one. So in blue, we have an example from a financial news data set. And it's categorized as a neutral example. It's neither positive nor negative. Now the model has figured out how to change that to make it positive to the sentiment analyzer. But if you read the sentences, they're probably, a lot of them are still more neutral. So this is a valid adversarial example. Likewise, the second examples on your screen, the top, the bold one in red is a negative example. Then all the examples below that are categorized as neutral examples. Now, all these examples meet all the constraints. You might notice they're not exactly perfect. This is where one of those learning from human preferences kind of situations where if we had a whole data set of human preferences, we could really make this task very good. But not being open AI, I do not have that. So all I could do is just try to meet the set of constraints, and that's what they give in this example. So as the model trains, you can kind of watch it training and you can see all the behaviors which it tries. So let's have a look at a big list of examples of things the model tries. What does that mean? Okay. So at the top, is the original example. And then, so the model can paraphrase genuinely, but it can also, do things like synonym swap, change the cases. It can add punctuation, remove punctuation, ignore grammar, shuffle phrases. It can, do things like add phone numbers to the end of sentences. It tries that. It can add Unicode characters into sentences like square root signs. It learned that it could start every sentence with the word although, and it would screw up the sentiment. So that's quite interesting. Then it could also, it learned at one point that it could change the language of some of the fragments and induce misclassifications that way as well. Finally, you can do things like ask rhetorical questions and double negatives and all that stuff too. So that's some of the interesting things which it learned. Unfortunately, I'm running out of time. So we did a bunch of experiments. I'll show you the interesting stuff. So what we did is we tried like 4 or 5 decoding methods, and we tried a bunch of exploration parameters, and we ran it over several data sets. We found that using beam search was quite a good decoding method, but that we really kind of shined when we used diverse beam search. And adding diversity to the paraphrases just helps, because you can have a lot of different variation in your paraphrase set, and you're not generating the same stuff over and over and over again. So that kind of gave the best results. We compared it to a bunch of those optimization token modification algorithms I showed you before, and we found that, well, those token modification attacks did pretty well in terms of attack performance. In fact, I beat our model, but our model was much quicker because it doesn't have to solve the optimization problem, and it can generate 20 examples where the other one can generate 1 in much quicker time. So that's a win of sorts for our model. Yeah, that's more or less it. Happy to take questions now.
Any questions?
Thanks for the great talk. I have a question. Why use reinforcement learning here? Why not try something simpler like a adversarial training scheme?
As in, like, why didn't we just backpropagate?
Is reinforcement learning really necessary? Why use it?
We assume that we don't have any access to the victim model in terms of its parameters or its architecture. All we get is like the confidence intervals and stuff. So
right, so it's not a white box attack.
Yeah, it's a black box attack. So we
see.
can't access any of the gradients from it. If we assume we have access to the internals of the victim model, then we can. It makes much more sense to use a white box attack like you suggested, because it's just much more efficient.
I see. Thanks.
More questions? I have a question for you.
Sure.
So when do you stop degrading the model? When do you consider that the attack is being successful?
We train until we use like a validation set, and we track the number of successful attacks in the validation set, and we use early stopping when, you know, there's a point where the model starts to overtrain and you can really see the performance drop off a cliff. And we just use an early stopping criteria using like attack success percentage on the validation set.
Thank you.